Okay, today I want to talk about power series. So we've talked about series of numbers, trying to add up an infinite bunch of numbers. Now we're going to put variables into it. So we're going to look at expressions of this form: summation from 0 to infinity of Cn x to the m. So C sub n is some number. X is a variable. So this is called a power series expanded about 0. And more generally, you can look at, instead of x to the n, x minus a to the m. This is called a power series expanded about a. So a is just some number. Again, these are numbers, and of course the x is a variable. So you sort of think of these as polynomials, except that they go on forever. They go from 0 to infinity. So they're polynomials, but they just continue forever. So then kind of infinite degree polynomials. Well, that's not really a polynomial, but it's kind of like a polynomial. Now look, if you picked a particular value of x and plugged it in here or here, then you would just get a series of numbers. So that's what we've been talking about for the last couple weeks. And so it either converges or diverges, and you have various tests and so on. So for a given power series, you might imagine for certain values of x it'll converge, and for other values of x it'll diverge. So those values of x where it converges gives you a function. You plug those values of x into the function and you get back a number, whatever this converges to. But the domain of the function is only those values of x where we have convergence. So a natural question is, what are the possibilities for the domain? Can it be really weird that it converges for certain values of x but not for others, and they could be a strange set where they converge? Well, it actually works out pretty simply. So let's look at some possibilities. We'll look at it by looking at some examples. So we're trying to figure out what's the set of values of x where the series converges. Again, so if you took a particular value of x and you plugged it in here for x, you'd get a series of numbers. And then that's convergence in the sense we've been talking about. And we want to know which values of x give you convergence. All right, so here's like the worst case. Here's a bad situation. Summation 0 to infinity n factorial x to the m. Let's apply the ratio test. The n plus first term is up here. The nth term is there. The factorials all cancel except for that. And the powers of x all cancel except for that. Now, if this is not 0, then this expression goes to infinity as n goes to infinity. And remember, for the ratio test to give you convergence, we have to have that this limit is less than 1. So it diverges at every point except, well, if x equals 0, then of course all the terms are 0 and it's not very interesting. So here's this power series converges only at the value 0. So that's pretty bad. Now on the other hand, let's look at the best case. Let's just look at this power series. So now the nth term is x to the n over n factorial. Here's the n plus first term. Here's the nth term. Take the ratio. The powers of x cancel, leaving absolute value of x up top. The factorials cancel, leaving an n plus 1 now in the denominator. And now as n goes to infinity, this goes to 0 for all x. So we have that this converges for all possible values of x. So that's like a best case scenario. Here's a worst case scenario. Then there's an intermediate case, sort of in between best and worst. For instance, look at this example. So this is a power series expanded about the number 2. Powers of x minus 2. And then they'll all be divided by square root of n. So again, the ratio test. N plus first term, nth term, absolute value of the ratio. The powers of x minus 2 cancel, leaving just this. And these guys give you that. And we know from we've known for a long time that something like this goes to 1. This guy goes to 1 as n goes to infinity. So the entire thing goes to x minus 2 absolute value. And if you want to have this converges, you need to know from the ratio test that's less than 1. So that's what we have here. If the absolute value of x minus 2 is less than 1, we know we have convergence. So that just means that x is between 1 and 3. Now, on the other hand, if x is bigger than 3 or less than 1, that's the case where this expression will be greater than 1. So you get divergence. What about if x equals 1 or x equals 3? See, that's the case. If you plug in x equals 1 or 3 here, this thing would equal 1. And remember, that's the situation for the ratio test where it just depends on the example. So, for instance, for this example, if you plugged in x equals 1, plug it back into here, then this becomes negative 1. So you get that. But that's an alternating series. The terms alternate plus minus, and the terms are all 1 over square root of n, so they're decreasing to 0. So the alternating series test says it converges. On the other hand, when x equals 3, plug x equals 3 back into this, then this is 3 minus 2, so that's just 1 to the n, or 1. And you get this series. And we know that diverges because it's a p-series with p as a half. So the way to think of this is we're expanding about x equals 2, and we're going to go distance 1 on either side, because that corresponds to the absolute value of x minus 2 less than 1. Right? Because, again, you think of absolute value of x minus 2 as measuring the distance from x to 2. And we want that to be less than 1. So that says x is allowed to stray no more than 1 away from 2. So it could go up that far and go down that far. So when the inequality is strict, when x minus 2 is less than 1, and that's when x goes from 1 to 3, we get convergence. So that's convergence inside this interval. Outside the interval, we get divergence. So that's where x is less than 1 or x is bigger than 3. And that corresponds here to this absolute value being bigger than 1. So we know from the ratio test you have divergence. But when it equals 1, that's at the endpoints of this interval. And it just depends on the example. In this example, we got convergence at this endpoint, but divergence at that endpoint. In other examples, it could work differently. You actually have to look at the examples case by case and plug in the one endpoint, plug in the other endpoint, get series which hopefully you'll recognize, and you can decide whether or not they converge or not. So in this example, we say the radius of convergence, that's like the radius, sort of how far from 2 are you allowed to go? And in this case, it was 1. We could go 1 on either side. So in this case, the radius of convergence, which they use capital R for, is 1. The actual interval convergence is this, because it converges at 1, does not converge at 3. So it's like a half open, half closed interval. And the very nice fact about these power series is the following theorem. The theorem basically says these three examples are essentially the way it works. So given a power series, there's exactly 3 possibilities. It converges only when x equals a. That's like the worst case. You could think that the radius of convergence is 0, because you're not allowed to go anywhere. If here's a, you're not allowed to stray away from a at all. It only works at the one point. So that's bad. Here's the best. It converges for all x. So you could think of, if here's a, how far can you go on either side? You can go forever, because we have convergence at all points. So think of the radius as being infinite. And in the intermediate case, is some finite number somewhere between 0 and infinity, and if x is within distance r of a, we have convergence. If if the distance from x to a is greater than r, we get divergence. And at the endpoints, again, it depends on the example. You have to look at every example individually. So the theorem, that's what the theorem says, that these are the only three possibilities essentially embodied by these three examples I was showing here. So given that, if you have a power series, then that determines a function as long as x is in the interval of convergence. Right? Because if x is chosen in the interval of convergence, then this actually converges to some number, so you get a function. Right? You give me a number x, I have to give you a number back. What number do I give you back? I give you this number, because we know it converges. So it converges to some number. You may not know which number, but at least it converges to a number. All right, now as I was saying before, these expressions kind of behave like polynomials, and here's the real more precise way in which they behave like polynomials. So this theorem is a very powerful and useful theorem that tells you, given a power series, and let's assume that the radius of convergence is bigger than 0, so it might be a finite size interval, or it might be an infinite size interval, either one. Then on the interval of convergence, this basically says you can differentiate and integrate these functions kind of as though they were polynomials. See, this says here's my function given being my power series. If I want to take its derivative, what this says is I just differentiate it term by term. I just go inside and have the constant Cn times this derivative, which is n x minus a to the n minus 1. So this says I can differentiate the power series term by term. Now, you're used to doing that for polynomials, right? Because you know the derivative of the sum is the sum of the derivatives. But the difference here is this is an infinite sum. So we've never ever discussed this before. Is the derivative of an infinite sum the infinite sum of the derivatives? Well, at least in the case of these power series, it is. And the same for integrals. So if I want to integrate this series, let's put a dx here, I integrate term by term. So it's these cn's times, then I integrate x minus a to the n in the usual way. So this is think of this as the integral of a sum is the sum of the integrals. This is the derivative of a sum is the sum of the derivatives. Or we say you can differentiate and integrate term by term. So that's very powerful, extremely useful. Of course, it's only valid inside this interval of convergence. Outside the interval, well, you don't even have a convergence series, so it doesn't define a function. And on the endpoints, when x is a minus r or a plus r, then these are not valid necessarily. You're only guaranteed that these are valid inside this interval. But again, informally it says you can differentiate and integrate term by term. So let's look at some examples of that. Okay, so let's look at some examples. All these examples are basically being generated by a geometric series. And then this stuff over here I talk about differentiating, integrating. So let's start with the basic geometric series. Look at the power series. Summation n goes from 0 to infinity of x to the m. It's like 1 plus x squared plus x cubed and so on. There's a geometric series. First term is 1, the ratio is x. So it converges to 1 over 1 minus x if the ratio in absolute value is less than 1. So note that what that tells us is this function, f of x equals this function, can be represented by this power series as long as the absolute value of x is less than 1. All right, so this is from x running from bigger than minus 1, less than 1. So that's your basic geometric series. Now we're going to do some modifications. First, I want to replace x by minus x. That would give me this. So if I just replace every occurrence of x by a minus x, the function becomes that, the power series becomes that, which I get the same power series, but the signs are alternating. So here's a power series representation for this function, again valid in the same interval. Now integrate. Let's integrate. And if I can integrate this function, let's not worry about the constant of integration. When I integrate this function, I get the log of 1 plus x. But from this result here about term-by-term integration, that's the same as integrating these term by term. So I get x squared over 2, x cubed over 3, x to the 4th over 4, and so on. And I get this alternating power series for the log of 1 plus x. Again, valid in this range. So there's sort of out of the blue a power series representation for this logarithm function. Or I could replace every x by negative x squared. If I do that up here, replace x by negative x squared, I get 1 over 1 plus x squared. And I just replace every x by negative x squared. And that gives me this power series, just the even powers and an alternating signs. And now if I integrate that, this integral is inverse tan. Integrate these term by term. Again, the constants of integration will be 0 for both, so I don't have to worry about it. You can just check that, say, for x equals 0, this gives the correct value. So that means the constants of integration are good. So integrate this term by term, and I get this power series. So there's a surprisingly easy way to find the power series for this crazy function. So if I wanted to use it, I could use it to evaluate the inverse tan function at certain values of x. Right, so this is all fine and dandy, but it's kind of limiting. What about other functions? Exponential, sines, cosines, etc. You can't really get them from this approach. This gives you some nice examples, but it's quite limiting. What do you do about them? Well, stay tuned. That's the subject of the next lecture. So we'll find out about that soon enough. So.